No nation which expects to be the leader of other nations can expect to stay behind in this race for space.
Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. We are all disappointed that Starship might be delayed until next year. This was not our hope, but we saw it as a real possibility. While many might believe that this is the work of a cabal of deep state evildoers, it is more likely to be the result of politics as usual. And there are serious environmental concerns for this area, just as there are for this one. But if we are going to have a space program, we need to be able to launch rockets. Single-stage to orbit space planes will never have the mass capacity of multi-stage launch systems. They are not supposed to. What they can do is transport high-value cargo, like human beings, in much greater comfort and safety than a vertical launch and landing rocket system ever will. A space plane can lose power and still glide to a survivable landing, something you will never see with Starship. That being said, we need to get massive payloads to orbit and the moon to start building the infrastructure that humans will need. Right now, the only hope for that is Starship. This is surprising, as any nation capable of building large ships or submarines could start building a massive launch system. We're looking at you, Norway. Where is my space cruiser? But progress is being made. A reusable second stage has been discussed for the SpaceX Falcon rocket system. They looked at parachutes and balloons, but personally, I've always liked the idea of auto-gyrating helicopter blades. Roton was a bad idea because they used helicopter blades at launch. That's not a very mass-effective way to gain a little altitude. But coming back down, I've always wondered about telescoping blades that could be deployed from the top of the second stage. This would act like a drogue parachute and help stabilize the ship. And it will also start to spin if the blades have a little angle to them. It's spinning in the wrong direction for lift, but it does provide a large effective surface area, slowing descent without power. Then just before landing you can reverse the pitch on the blades, which will continue to spin by inertia, allowing for a controlled landing. If you added an electric motor and battery pack, you could have even more control over the landing. Just a thought. Let us know what you think. But while the SpaceX Starship has been put on hold, other companies are making rapid progress. Firefly Aerospace just set a new responsive launch record. Just 27 hours after the U.S. Space Force contracted for the Victus Nox mission. Victus Nox is meant to mean conquer the night, and the goal is to get a launch off the ground within 24 hours. This is to make sure that Space Force can rapidly replace assets taken out by an aggressor nation. The spacecraft for this launch was built by Millennium Space Systems out of Virginia. This company specializes in small satellite prototypes for surveillance and communications. These satellites are critical to missile defense and warning systems. Firefly accomplished the mission using its Reaver engine-equipped Alpha 1 first stage. We did a deep dive into Firefly Aerospace in June of 2021, with an analysis of the Alpha in September of the same year. Since then, there have been some changes. Here is the Elytra orbital platform. This comes in a Dawn version for low Earth orbit missions, a Dusk version for going from LEO to geosynchronous orbit, and I wish a day version so we could stay with a Foundation theme. But no, this is the Elytra Dark, used from transfers to lunar orbit and beyond. This is a lot like the Photon system made by Rocket Lab. And these orbital and transfer control systems are innovative and essential additions to any serious launch system provider. Firefly is also making the Blue Ghost lunar lander. This lander will have a mass of 94 kilograms, and NASA awarded Firefly $93.3 million to use the Blue Ghost to deliver 10 science and technology instruments and experiments to the lunar surface as part of the Artemis program. The lander will come down near Mare Crisium sometime in 2024. It will operate during the 14 Earth Day period of lunar sunlight, that I like to call dayloon, and as far into the night as it can make it. The Alpha rocket burns RP-1 and liquid oxygen, much like the SpaceX Falcon 9, but is much smaller, at just 29 meters and 54 metric tons, than the Falcon 9's 70-meter 550-ton size. This was the second successful launch of the Firefly Alpha. The next great thing came from Stoke Aerospace. This company was founded by former SpaceX and Blue Origin engineers. Don't ask me how they got along. They have been able to raise over $75 million so far, and have been given control of Launch Complex 14 in Florida. LC-14 was used to put the first American, John Glenn, into orbit. We did a deeper dive into Stoke earlier this year, when they were building and testing their 15-thrust-chamber aerospike engine. This design is used with a blunt re-entry second stage, and uses differential thrust for vectoring. The base of the Stoke second stage is cooled by releasing super-cold liquid hydrogen in a space between the heat shield and the base of the spacecraft. The cryogenic fuel can protect the second stage, allowing it to come back and land. To test this system, Stoke decided to hop its second stage, much like SpaceX did with the much larger Starhopper. As many of you point out, the idea for Stoke's system has been around a long time. But making something real is what counts. And if all goes well, Stoke will have a methane-fueled first stage powered by 7 rocket engines and a fully reusable hydrogen-fueled second stage. That will make this a fully reusable rocket system, just like Starship, able to return things from space and land vertically anywhere on Earth. Or even, if they were to add a larger booster and make this a 3-stage ship, on the moon. But what should be launched first to the lunar surface to start a new colony? We have done many lessons on the need for nuclear power in space. And to help solve this problem, scientists around the world, including the United Kingdom, have been working on these power systems. The Nuclear Futures Institute in Wales has been given a contract by NASA to develop a micro-reactor for use on the moon. This reactor will use Triso pellets, which stands for Tristructural Isotropic Particle Nuclear Fuel Pellets. Let's learn about how these Triso pellets are made and used.
Triso, the most robust nuclear fuel on Earth. Incredibly small and tough enough to handle the extremely high operating temperatures of today's advanced nuclear reactors. Triso is a dream for some, but a full-scale production reality for one. BWXT is the only U.S. company to manufacture a radiation-tested uranium oxycarbide Triso fuel using production-scale equipment. Our specialty fuel facility in Lynchburg, Virginia, perfects fabrication techniques and manufactures the fuel required for the development and production of safe, compact nuclear reactors needed to meet growing energy needs. Our Triso production process begins with solution preparation, where feedstock of any enrichment is dissolved in nitric acid. The feedstock batches are then blended to obtain the correct enrichment. Blended uranium and proprietary organic solutions are mixed and added to the forming station, maintaining specific temperatures to inhibit the gelling of the liquid. The solution is forced through an orifice to form spherical particles that are then hydraulically transported from the forming column to the collection vessels. After the kernels are formed, they are washed and dried. In the sintering process, kernels are placed in a fluidized bed reactor, heated in a hydrogen-argon environment, and held, assuring water or hydration is removed, and uranium oxyhydroxide is converted and reduced accordingly. The kernels are again heated in a carbon monoxide-argon environment, where they are then fully densified. Next, the material is separated by size, ensuring precise specifications are met. This material enters the Triso coating process, where 4 coating layers are deposited in a single furnace run. In overcoating, the Triso particles are layered with a mixture of graphite and resin. We then begin the compacting process to take the overcoated Triso particles and form them into circular cylinders under heat and pressure. The compacts are loaded into graphite boats and heat-treated in an atmosphere of purified argon, driving off any volatile components from the compacts and densifying them. By the end of this process, we have successfully produced Triso fuel compacts. Our existing Triso fuel production line and ongoing increases in capacity allow us to meet emerging technology demands, including microreactor, space reactor, and civil and commercial advanced reactor applications. BWXT owns and operates the only NRC-licensed facility authorized to handle and process highly enriched uranium and capable of fulfilling all Triso-related needs, from feedstock preparation to uranium recovery and purification. Capable, experienced, and licensed, BWXT is producing the fuel of the future today.
This little guy packs a big punch. It's the size of a walnut and can release the same energy as 2,000 liters of diesel. Not bad for a rock. With so much power comes great responsibility. For as fission reactions take place, the uranium fuel is slowly transforming into roughly 1/3 of the periodic table as solids and gases. These are the radioactive fission products that make nuclear waste dangerous, and they must be permanently contained. So beyond generating heat, the fuel needs to trap the fission products in place. In FCM fuel, millimeter-sized bits of uranium are trapped in tiny ceramic pressure vessels that can withstand extreme temperatures and radiation. These particles are then encased within a fully dense silicon carbide matrix, somewhat like encasing the fuel in a diamond. Silicon carbide is used for tank armor and has an extremely high melting temperature, far beyond the heat generated by the fuel. It is particularly resilient to radiation and does not chemically interact with other materials in the reactor. If the pellet is fractured, the fuel particles can remain intact as they are smaller than the smallest fragments. The core is assembled with enough fuel and graphite blocks to produce heat through self-sustaining fission reactions. This fully ceramic core has the lowest power density of any commercial reactor ever, allowing it to easily dissipate excess heat. To power it up, control rods are withdrawn and the fission reactions can begin. But these reactions slow down at higher temperatures. So to keep producing power, the reactor has to be cooled. If cooling stops, the reactor automatically shuts down. Helium carries heat out of the nuclear core. It is a harmless, noble gas, completely unreactive and stable. And while somewhat inefficient, it is the safest coolant available. Now, the problem with nuclear fuel is that it continues to generate heat even after the reactor is powered down. It will continue to generate roughly 10% of the original heat for hours and days to come. And if it's not cooled, that heat will pile up. The challenge with nuclear has always been to ensure the reactor does not damage itself when cooling is lost. The MMR can dissipate all excess heat passively and harmlessly into the environment in any scenario. Like a warm puck, it cools off just by sitting there. No moving parts or fluids, no operator actions, just simple cooling by conduction and glowing. This means the reactor can tolerate extreme conditions and survive undamaged. It can deal with complete withdrawal of all control rods. It doesn't need power to operate cooling pumps or emergency systems. The MMR doesn't even need coolant or natural airflow to stay at safe temperatures. It doesn't really need very much at all. Instead of designing elaborate safety systems against particular scenarios, we've designed a reactor that is inherently safe no matter the events. The MMR harnesses the fuel's formidable energy while fully containing its radioactivity during all encountered conditions, be it normal operations, worst-case failures, or permanent storage.
These pellets can be used in many different high-temperature gas-cooled and fluoride salt-cooled reactor designs, including the eVinci microreactor, built by Westinghouse. The eVinci is a very compact, all-in-one nuclear power plant, designed for use in remote locations. This device is basically a solid-state power system that can be fit on the back of a large truck, or the cargo hold of a Starship. NASA is already evaluating this technology for use in space, as it would be perfect for a lunar base or a base on Mars, providing up to 5 megawatts of thermal and electrical power for up to 8 years without refueling. But to get things started, NASA has hired the Nuclear Futures Institute to build the Space Flower Moon Microreactor. This reactor will also use Triso pellets, in a system designed by Rolls-Royce.
Rolls-Royce has been busy building this nuclear microreactor. It's a whole new classification of reactor, and one the company says could eventually provide power for NASA's planned base on the Moon.
We are in a new space race. There's a lot of commercial opportunities, but also agencies having aspirations to go to Moon, stay there and beyond. So what we're looking at here is a scale model of our microreactor core system, core technologies.
Perhaps better known for its engines, British engineering firm Rolls-Royce has spent more than 60 years quietly building the power plants for the UK's fleet of nuclear submarines. The experience, it hopes, will help it compete in the new space race, according to engineer Matthew Marriott.
There's a lot of commercial opportunities, but also agencies having aspirations to go to Moon, stay there and beyond. But really, in order for everyone to do that, they need power and reliable power. There are power options in space, solar electric being a good opportunity. But there are instances where solar isn't a viable option. It can't deliver you the power that you need for space. So this product that's sat here behind me will enable all of these companies to realise their ambitions in space.
NASA plans to establish a base on the Moon as a stepping stone for eventual human expeditions to Mars. Astronauts would go there to learn the skills needed for deep space missions. Sustaining human life and a habitat on the Moon requires a serious amount of power, which is where products like microreactors come into play.
2 years ago, if you'd said to me we'd be looking at designing reactors to go on the Moon, I'd have said that you were absolutely barking and it was a crazy idea.
Abby Clayton is Director for Future Programmes at Rolls-Royce.
When you think about Mars, is a really, really long way away, so it can take up to 18 months effectively to travel to Mars using conventional types of fuels. If we kind of use the power of nuclear to do that, you can probably cut that to around a 3-month period to travel to Mars. So it actually makes that planet more accessible for us to actually go and explore, make sure that we can do experiments there, but again also work out, can humans get to Mars? And that's certainly the plan, by 2040 is a target out there to get humans on Mars.
Microreactors designed for space will also have plenty of uses on Earth too, says Gary Jones, Head of Manufacturing Innovation.
It can be used for disaster relief, so you could actually transport one of these systems in within a short time frame, hours rather than weeks, to re-establish a grid, and then you could have power from a box that would really help disaster relief. You could also replace diesel electric generators to help decarbonise a multitude of applications.
And power systems aren't the only use for this technology. BWXT is partnering with Lockheed Martin to build an advanced nuclear thermal rocket system that can get us to Mars in just 3 months instead of 9. These amazing power systems are a perfect example of how space technology can get us through the cold lunar night and open up the rest of the solar system to human colonization. We don't need to wait for fusion. And now let's listen to a lecture on how this wonderful technology works.
So the talk is on nuclear propulsion in the UK. It was a collaboration between Lockheed Martin UK and Rolls-Royce up in Derby. And obviously, presented it a couple of times, but it's been a few years since I've done it, so hopefully I can do it justice. So just a bit about me. So I started my career at the University of Bath. I first applied there to do mechanical engineering. So I did that for 2 years and then went to Honeywell Aerospace in Yeovil. And down there they do sort of environmental control systems and life support systems for civil and military aircraft. So I was a structures analyst, so I worked on stress analysis for those pneumatic systems. So it's taking bleed air from the compressor in the engine, passing it through valves, heat exchangers, rotating compressor turbine assemblies, water separators, things like that, to pressurize the cockpit and cabin, and also provide oxygen for the fighter pilot themselves. Once I returned back to uni, I realized aerospace was for me. So I transferred to aerospace engineering, did a couple of years in that. And as part of what I learnt during my industrial placement, I actually entered a competition in my third year, which was run by an Indian company called Team Indus, and they were creating a lunar lander as part of the Google Lunar X Prize to land a rover, lunar lander on the moon, deploy a rover, take pictures, send it back to Earth. And as part of that program, they set up a competition called Lab to Moon, which was a student competition to create a payload for their lunar lander and do some useful science. So my project was called Lunar Dome. It was an inflatable habitat that is the size of a soda can, and it inflates a flexible material to atmospheric pressure, maintains it for as long as possible. So yeah, we entered the competition. There was 3,000 entries, and we ended up coming third. So we got a contract to put the experiment on the lunar lander. And yeah, the rest is history. So yeah, after I left my fourth year at uni, I did a summer internship at Airbus Defence and Space in Portsmouth. So they manufacture large telecom satellites for civil and military applications. So I was working in the mechanical design office, working on design of the payloads that go onto the satellites, also looking at stress and thermal analysis, looking at launch conditions, and then in-service conditions, trying to make sure that everything can be signed off and put onto those large satellites. Once I left uni, I joined Lockheed Martin. So I started as a graduate engineer, did that for 2 years, rotating around the business. There's quite a wide variety of different roles you can do. So I started off in land vehicles, did a couple of rotations there, and then moved to the more aerodynamic side of things, modeling and simulation, which is kind of what I do now. Been an associate member of the Royal Aero Society for a couple of years now, and through that I have won that NE Row medal. So that's pretty much me. So bit of a disclaimer to start with. We always have to do these as part of these presentations. So the views and opinions expressed here are those of the authors and in no way represent the views, positions or opinions expressed or implied of my employer or anyone else. So getting on to the meat of the presentation. So nuclear propulsion. A lot of people don't know that nuclear propulsion for space applications has been around for a long time. NASA started investigating nuclear propulsion in the 1950s to 1960s. Their kind of flagship program was called the NERVA, so the Nuclear Engine for Rocket Vehicle Applications. And this was kind of a test program where they produced hardware, load of static fires on the ground. So they used a hydrogen fuel source, passed it through a nuclear reactor, or a converging divergent, to measure efficiencies, thrust, and all sorts of different parameters. So the kind of basis for this study was a couple of things. So NASA in 2021 published a request for industry to develop nuclear space propulsion technologies. So that's nuclear thermal propulsion and nuclear electric propulsion, which I'll get into more detail a bit later. So that came out in 2021. There's been a load of contracts that have been given out since then. And recently, there's been a lot of investment in there in the past couple of months. Elsewhere in the world, China have announced that they're planning to produce a nuclear-powered space shuttle by 2045. And the real meat of this presentation is about Rolls-Royce and their development. So in 2021, they produced a kind of roadmap for the UK to expand their technologies within the space industry. So I think at the moment, the UK takes about 4% of the space industry globally. And by 2030, they want to expand that to 10%. And Rolls-Royce are going to be a big player in that, especially on the nuclear side of things. Okay, so purpose of this study. So as part of the Project on Nuclear Issues conference that we presented in, we get a chunk of hours to do a kind of standalone study to assess something, write a presentation, then write a paper on it. So what we decided to do was investigate a comparison between conventional propulsion systems and nuclear propulsion systems in transporting both cargo and people from Earth to Mars. We looked into mission profiles around the mid-2030s, and we were kind of comparing two kind of major quantitative values, measures of how good a system is. So with cargo missions, obviously, you want to transport as much payload as possible to the surface. Once you're there, you can then, if you've got a lot of mass there, you can bring a lot of science equipment, bring building materials, tools to create a habitat, create a base, create infrastructure, things like that. So we want to maximize the payload to surface in the cargo missions. In the manned missions, we want to minimize transport time. So that's for two reasons. One is to reduce the passengers' exposure to cosmic radiation, microgravity effects, which can affect your sort of bone density, your muscle loss, etc. But also because transfer times typically take in the order of six to 7 months. So who wants to be in a spacecraft for 6 to 7 months? Definitely not me. So trying to minimize that is beneficial. So next few slides, I'm just going to go through kind of a basic overview of different types of propulsion systems. So starting with sort of chemical, conventional, liquid-powered rockets. So schema on the top right, we've got two different tanks. You've got your fuel tank, which typically contains combustible materials such as liquid hydrogen or something like kerosene, RP1, if you know about rocket fuels. And then you've got an oxidizer tank, which is pretty much solely there to initiate the combustion and maintain the combustion process. So typically that's liquid oxygen. So benefits of these systems, you get very high thrust, so they're effective at both sea level and in a vacuum. So depending on your configuration of your nozzle, you can have your first stage to launch the rocket off Earth using a nozzle that's configured specifically to work in the atmosphere. And then you've got your second stage typically has a slightly different nozzle, which is configured to work in a vacuum. So the way you sort of, this kind of flows is you've got your two liquid propellants, they flow through the pipework that's in the system, goes through a couple of turbo pumps to increase the pressure as it goes into the combustion chamber. Once it's in the combustion chamber, the gases combine, the combustion process is initiated and maintained, and then it flows through a converging, diverging nozzle to convert thermal energy and pressure into velocity, which is then reacted back through the rocket and produces thrust. So another benefit of this, these types of systems is once you actually get to Mars, the fuels that you use are actually quite easily manufacturable. So both on Earth and Mars. So with this example I've got here, the SpaceX Starship, they use methane and oxygen. And there's quite simple chemical processes on both planets to be able to produce both fuels. So yeah, it's beneficial to be able to use those. The major downside, of course, is got a useful fuel tank and pretty almost redundant oxygen that you're using. So you normally have a 6-to-1 ratio between the masses of each. So ideally, if you could remove the oxidizer tank and remove the oxidizer that's in it, you can replace that with useful payload. So example I've got on there of a contract that's recently been awarded to SpaceX. So I think, yeah, 2021, NASA awarded them a massive $3 billion contract to develop the Starship to carry humans to the moon as part of the Artemis missions. And in the future, they might be developing that into going to Mars as well. So getting onto the nuclear side of things. So it's two main types. So the first is nuclear thermal propulsion. And essentially it works in a similar way to the conventional case. except you've only got one fuel, so typically you use hydrogen, and you pass that hydrogen through a similar kind of pipework, turbo pumps, and then the main difference is that you've got a reactor, a nuclear reactor, instead of a combustion chamber, and the nuclear reactor generates heat, transfers that to the, and then again it's expanded through a converging diverging nozzle to produce thrust. Compared to conventional systems. No oxidizers required, so there's no oxygen there in the process at all. So as I mentioned, you get huge mass saving, which can be replaced with useful payload. But then a huge downside is, despite the fact that you're transferring heat from the reactor to the fuel, you still transfer a lot of heat to the surrounding structure as well. So you get reactor temperatures in the order of thousands of Kelvin, and you need to do something with that heat. So you kind of need to design some quite complex cooling systems for the structure to ensure that everything stays intact, I guess. So yeah, example I've got there, a recent contract that's been awarded by DARPA to Blue Atomic and Lockheed Martin in the US to design a nuclear thermal propulsion system, which I believe is planned to be flight tested around in Earth orbit by 2027. It's a $27 million contract, but I think last week NASA has announced that they're going to be joining forces with DARPA in this contract, and they're going to be plowing a lot more money into this development. So I think it's an undefined amount of money at the moment, but guessing it's going to be comparable to the ones we see with SpaceX. So finally, nuclear electric propulsion. So the main difference here is instead of using the nuclear reactor as a heat transfer source, you use it as an electricity generator. So the way the thruster works is you start with the electricity coming off the reactor, comes through an electron gun, so you've got electrons being fired. Then you've got the fuel coming around the outside of it and coming into the thruster as well. Typically, these fuels are inert gases such as xenon or krypton, which are much heavier than hydrogen or methane as typical fuels for the other two systems. So once the gas gets into the thruster, the electrons collide with the atoms in there, and they knock off electrons from those atoms to ionize them. And then those ions are accelerated through a magnetic field and an electric field to really, really high speeds. So you can get close to relativistic speeds, around 10% the speed of the speed of light. And then they're ejected out of the thruster. And there's a secondary neutralizing electron gun at the top, which then fires additional electrons back at the ions to neutralize their charge. That's the way that produces thrust. So typically you get a huge amount more efficiency from these thrusters, so 10 times more than chemical. Huge benefit is there's very few moving parts, so it's a mechanical engineer's dream. Very simple to design from a mechanical perspective. But you get really good reactor uses on Mars. So because you're generating electricity with your nuclear reactor, you can essentially use that reactor to produce electricity once you actually arrive at Mars. So when you're producing your base, powering sort of rovers and things like that, you can use that useful energy there. So typically, I think reactors have lifetimes of around 10 years. So once you actually arrive on Mars, you've still got a huge amount of useful energy that you can use to use up. The downside is very low thrust. So typically have to use these engines for in the order of weeks or months. So when you're traveling through space, you have to have them on for a very long period of time to have any kind of meaningful velocity change of your spacecraft, which means that they're only really useful in vacuums. So you can't use them to launch from the Earth's surface and escape the gravity field. So that means they kind of have to be used in conjunction with the other two, one of the other two propulsion systems. So chemical or nuclear thermal to escape Earth. Then in your second stage, when you're already in a vacuum, you can then use these to their full potential. So then I've got an example of another contract which was awarded a few years ago to Astra to develop a variable impulse nuclear electric thruster. It's a bit smaller contract this time, $10 million. The kind of announcement that I mentioned in the last slide, where NASA are joining forces with DARPA. So not only are they investing in nuclear thermal propulsion, they're also plowing a lot of money into this technology. And this is the technology that Rolls-Royce are really interested in as well. So that was kind of a big focus for us. So as I mentioned, Rolls and the UK Space Agency are reviewing the UK's future in the space industry, trying to lay out a roadmap for us to expand our market cap. So not only are they designing reactors, they're also designing spacecraft structures and systems. So in this example, you can see the thrusters are on the left-hand side there, and the crew and passenger compartment is way down on the other side of the spacecraft. So the reason for that is for safety reasons. So you don't really want your humans to be close to your reactor. So separation is really useful in reducing the radiation dose. You can also put your fuels in between your reactor and your passengers. So that attenuates a lot of the radiation coming through as well. And then also you can use disc shields. So you can see these two black shields there, which are kind of high density material that also reduce radiation exposed to the crew. And then that long boom you can see in between the two, an example of how elaborate your cooling system has to be. So if you've seen pictures of the International Space Station, you'll see a load of radiators coming out of it. And this is a similar thing where we're trying to cool down our reactor and project a lot of that heat as radiation into space. So there's a lot that needs to go into actual spacecraft design. We're thinking about these propulsion systems. So going into a bit of the analysis of what we actually did in this study. So we started off looking at a case study of the Starship. So SpaceX to transport masses of humans from Earth to Mars. It's going to be a reusable spacecraft, so they're going to be launched back, and all of the structure is going to be reusable. So working through this kind of mission profile, we start off step one. So we've got a booster and Starship attached to the top of it, which is filled with passengers. The booster will launch into Earth orbit, and it will stay there for a while. Alongside that, we'll have fuel tankers that will launch. So it'll be boosters with a spacecraft that contains fuel as payload. They'll launch into Earth orbit at the same time. They'll then perform orbital refueling around the Earth. And then the boosters, obviously, when they separate, they'll return back to Earth again. Once the Starship, which contains passengers, is then fully loaded with fuel, we then look at step 4, your long duration transport to Mars. So step 4 typically takes 6 months. It's longest duration, longest amount of intensity on your engines, your fuel burn. So that's kind of the step that we're most interested in. That's the step you can get the most benefit out of using nuclear propulsion systems. So once you've arrived at Mars, you'll then perform a landing burn. You'll land on Mars. You will perform your mission. And as I mentioned earlier, it's quite easy to produce fuels once you actually get to Mars. So you can do in situ propellant production. All this time, we're going to have more and more ships landing. Build up the number of people we've got, the amount of infrastructure. Once we have good production facility fuel, we'll then be able to refuel our spacecraft, return back to Earth, and then redo the whole process. So as I've said, step number 4 is the most interesting from a nuclear propulsion perspective. So that's the step we looked into as part of this study. So at the bottom there, we've got our cargo mission and human mission. So this is quite an old diagram. I think it's from 2016. But at that time, SpaceX were predicting with a cargo mission, you can take 200 tons of useful payload to the surface per mission. And with human rated missions, you can take up to 100 passengers. So with all that in mind, used a bit of software that we could estimate the difference between the chemical propulsion system and the nuclear propulsion system to perform a mission to Mars on that step 4. So we used a bit of software called GMAT, which is available open source, and we have on site at Lockheed. Our assumptions were that we used the Starship conventional system, and we compared that against the nuclear thermal propulsion system with the nuclear reactor designed by Rolls-Royce. Further assumptions, we assumed it was a one-way interplanetary trajectory only. Essentially, the return leg gives you the same benefits, so we only looked at one way. We assumed that the spacecraft mass, prime mass with no fuel in it at all, was identical between the two systems. We do acknowledge there's a shape difference because of all the safety things we were talking about, separating the passengers away from the reactor is quite an important thing to consider. And then finally, we assumed impulsive maneuvers. That means that when you perform maneuvers with your spacecraft, the velocity change occurs instantaneously. So there's no time duration while you're burning your fuels. You just assume that you go from one velocity to another velocity in an instant. So looking at the diagram we've got there, we've got the sun in the middle, and then orbit, and the outer ring is Mars's orbit. So we've got two maneuver points there. We've got TOI, which is called a trans-orbital insertion. So once you're in Earth orbit, you perform a burn to escape Earth's gravity, and then you go in that origin trajectory towards Mars. Martian orbital insertion maneuver, where you flip your spacecraft in the other direction, burn your engines to slow down, and then you get captured in the Martian gravity well. So essentially, because obviously Earth orbits the sun at a different rate to Mars, you need to be able to time this transfer really well. So ideally, you'd want for Earth and Mars to be right next to each other on the same side of the sun. So here and here. Obviously, Earth is rotating around the sun, so is Mars. So Earth, you want them to be close, and then they kind of follow each other, get closer and closer, and then once you get to that position there, that's where you land. So the way we kind of worked out these timings, we used the NASA design reference architecture for Mars, which kind of said when each technology is available. So roughly in the mid-2030s is a good spot to perform these kind of missions. We then looked at the NASA's trajectory browser, which is an online tool which tells you, basically tracks the relative positions of Earth and Mars. It kind of says what is the most efficient time to leave Earth to get that really nice trajectory up to Mars. And we resulted in a cargo mission of 2035 and a crewed mission of 2037. So typically you get these kind of 2-year gaps, just because of the way the orbits work. 2 years is typically the difference between useful trajectories. So running all of that information into our software, we're looking at a cargo mission in 2035. So there's a few assumptions that we've made here. So as I said, dry mass is the same. The Starship with all of its fuel loaded up. So our assumption basically says we're going to drain the ship of all of its fuel. The mass that's remaining, we're going to keep that the same. Refill it with nuclear thermal fuel, so liquid hydrogen. The comparison between the fuel mass there is massive. So because of that oxidizer that uses up so much volume, we can remove that, fill it all with hydrogen, much lighter fuel, gives you a much lower fuel mass. Then you can perform your mission, pairing conventional and nuclear. We get a payload to surface increase of about 20% with nuclear thermal. So that's without optimizing any of the structure, any of the actual design of the spacecraft. You get a pretty significant increase in payload. So then with the crewed mission 2 years later, so we kind of tackled this in a slightly different way, where we make the same assumption about the dry mass. We're going to take 100 passengers in both conventional and nuclear thermal. Same assumption about the fuel mass, but this time because we want to calculate the maximum velocity change that we can get out of our spacecraft. So running through the numbers, we can see that even with a much smaller fuel mass in nuclear thermal, we get an even higher total velocity change, which allows you to escape Earth's gravity, get to a much faster velocity in the mid-course, and then once you get to the Martian surface, you can still slow down, be captured by the gravity, and that maneuver much faster. So I think in the conventional case, it was around 6.5 months. In the nuclear thermal, it was about 5.5. And again, that's without optimizing anything else about the spacecraft itself. It's just comparing fuels. So here's a kind of visualization of how that looks. So on the left, we've got conventional trajectory, and on the right, we've got nuclear thermal. So you can see that with conventional, it takes much longer. Earth and Mars travel a lot further in that trajectory, whereas in nuclear thermal, we get a much more aggressive trajectory where we're increasing our radius from the sun a lot quicker. We arrive at Mars a lot quicker. And all those good things about reducing radiation dose, reducing gravity related physiological effects is beneficial for the passengers. So that was kind of the scope of the technical side of our study. So obviously we've only compared conventional and nuclear thermal. If we were to do this in more detail, so we've only looked at that step 4 in that mission profile. In reality, if you were to design a mission like this, you'd have to consider the initial orbit around Earth and final orbit around Mars. And each of those have 6 different variables that you'd need to optimize. So in total, you'd have 12. And then you've got that transfer as well. So it's a much more complicated problem once you start building these additional maneuvers up. So that was out of scope of what we did. But if you were to design a proper mission, you would do those kind of numbers properly. So the other thing was in this GMAT code, you can kind of decide what level of complexity you want in terms of which bodies you include in the solar system. So here we only looked at Sun, Earth, and Mars, but there's also many other bodies in the solar system that could have their gravitational affecting the spacecraft. So if you were, again, to do this in more detail, then you would include those extra bodies. So then kind of missed out nuclear electric in this. So the reason for that was that assumption about impulsive maneuvers where our velocity change with nuclear electric, because you're basically thrusting your spacecraft for weeks or months, that assumption is no longer valid. And it makes the analysis a lot more complicated when you're trying to burn for a long period of time, change directions, burn for another long period of time, and then arrive at Mars at the perfect spot, perfect velocity. So yeah, that takes a lot more computational power than we had. And also, as we were saying, you need a hybrid propulsion system typically. So to escape Earth, you probably need a conventional or nuclear thermal engine anyway. And then once you get to Earth orbit, you replace your second stage with a nuclear electric. So yeah, that obviously, as a whole mission, that will cause a lot more complexity in your design of your spacecraft, your equations that you're trying to solve. But having looked at some of the numbers you get from the efficiencies in thrusters, so I've kind of said with specific impulse there, which is kind of a measure of how efficient the fuel is and the engine system, typically get 380 with conventional, you get around double that with nuclear thermal, you get around 10 times with nuclear electric. So when we're thinking about the humans on board, we're looking at delta V budgets, change in velocity. You get a slight improvement with nuclear thermal, but with nuclear electric, you get 4 times more change in velocity, which would significantly decrease your transfer time from Earth to Mars. So, in conclusion, kind of already said, you can see sort of improvements on both cargo missions and manned missions using Rolls-Royce designed nuclear reactor in a nuclear thermal propulsion system to reduce your payload in a cargo mission by 20%, and you can decrease transfer time in manned missions by 17. Obviously, if you're designing a mission properly, increase. That's pretty much it. So I'll open the floor to questions. Hope you enjoyed it. Hope you found it interesting.
Also, any questions in the audience? I'll bring the microphone over.
Thank you. A couple of questions, really on the nuclear power plants, which is not really my field, but I get the impression from normal nuclear power plants that these are fairly slow to start up and to shut down. When you put the control rods in, to mitigate the fusion reaction, then it takes a long time for the thermal mass to decay. So I assume for this that you sort of light the fuse on this rocket and wait a week before you climb into it.
Yeah, so
sorry. And how does that work when you're in flight and you want to do another burn? Do you shut it down when you're coasting, or?
Yeah, so obviously kind of nuclear reactor side of things was Rolls-Royce's expertise there, so I'll probably give the best answer I can. So what I'd assume before you launch your spacecraft, you would initiate the fission reaction in the reactor before you launch. So by the time you actually get to launch, your reactor's already producing heat, it's already at the kind of equilibrium conditions that you need to be able to pass fuel through it. Second question is on, once you get into space, how do you stop a burn and then restart it? So I think that kind of comes with the cooling system. So what I'd assume is you would keep your reactor doing fission the entire duration of the mission at a constant rate, and constantly be rejecting heat while you're traveling. And once you need to relight your engines, you would then have the right conditions to be able to pass fuel through it at any time. So that's probably the best answer I can give without being an expert.
Right, and the follow-on to that really was the nuclear electric. You sort of said it was fairly simple with few moving parts, but my thing is that if you look at a standard nuclear power station, then yes, there is a big reactor vessel, but then alongside it, there are some enormous generators, all of which have got great big steel masses hurtling round and round with enormous gyroscopic effects. So with your, how do you generate the electricity? Is it a,
yes.
I know that electrical generation technology is what, 150 years old, but it's still got some fairly significant problems with it. And of course, working fluids, sodium or water, or?
So again, not an expert in nuclear power production. I do know there are systems out there that can convert heat to electricity directly. So think about Formula One cars when they do regenerative braking, they convert heat directly to electricity without the need of a working fluid. I don't know if that creates enough electricity to be able to power a thruster, but I'm assuming there's some clever new technology that has been developed to be able to eliminate the need for, maybe not eliminate working fluids entirely, but be able to generate it in some other form.
Cool. Any other questions in the audience? Okay, I'll.
Yeah, thank you for the presentation. I was just wondering, you mentioned earlier there was an assumption about assuming that the velocity changes instantaneously, and as we're looking at the propulsion systems where the thrust is becoming lesser and lesser, I imagine that assumption makes a bigger impact in the calculations for the mission, and I'm just wondering what systems or solutions are in place for readjusting the issues of the trajectory, I suppose.
Times of months. See, when you create a spacecraft, you've got some pretty high technology systems that deal with calculated trajectories. So with that assumption that we made with the impulsive maneuvers, it just makes the modeling process a lot easier. It is possible to model continuous burns, long duration burns. It just takes a lot more time, effort, computing power to do so. So I know that there's electric propulsion systems of satellites. So a lot of the time when a satellite's in orbit, it gets bombarded with solar radiation, which decays the orbit. There's also very low pressure gases up in space. So if the orbit is quite close to the atmosphere, you do get some drag, which kind of decays the orbit as well. So they do use electric propulsion on satellites to boost the orbit, where you burn your engine for a long period of time to get back to the position that you want your satellite to be in. So there are systems out there that actually do these kinds of calculations, and obviously you plan your mission in advance to be able to do those kind of maneuvers. So yeah, I mean, I've never done one myself. One of the reasons I recommended it for the future is because I think it's a really difficult problem, especially for interplanetary trajectories where you've got the Earth moving, Mars moving at a different speed. You need to really get that perfect position and velocity to be able to meet Mars at the perfect time. So it's a really difficult problem, but people have solved it before. So,
another question at the back. Sorry, I got a quick question for myself actually. So I sort of noticed a lot of the sort of things you used to sort of develop the mission architecture. Were you surprised at the amount of open source and readily available materials that allowed you to sort of develop and mission architectures?
NASA are really good at having things open source. So using their trajectory browser, using their Mars mission architecture, it's all open source stuff. They're really good at putting things out publicly. So I would say I was surprised. I have used NASA documents, NASA software before. But yeah, I mean, you can find a lot out on the internet these days. And yeah, I guess Rolls-Royce was a great help with that as well, because they've been researching these kind of things for decades. So they pointed us in the right direction really early on, which allowed us to take it as far as we did. So, yeah, I'd say I was.
Fantastic, thank you very much. We've got a couple of questions actually in the chat as well, so I'm going to quickly bring those up. So we've got a question from Student S. Okay. Hi. My question to Sam is: have nuclear reactors considered for long-term deployment missions such as the new space station, considering the ISS is scheduled to retire in 2030?
Yeah. So you mentioned SpaceX got the contract to develop their Starship to transport NASA astronauts to the lunar surface. As part of those Artemis missions, the latter ones are to develop something called the Lunar Gateway, which is a space station that's going to orbit around the moon. So we're kind of moving from having our astronauts within 400 miles of Earth in the ISS to having them permanently stationed on another solar body. The benefits of having a space station orbiting the moon is it's a good stepping stone to Mars. So once we have an established base on Mars, an established space station orbiting the moon, we'll be able to send spacecrafts to dock with the Lunar Gateway, refuel. Once you get to the Lunar Gateway, there's very little gravity to escape the moon's orbit, so it makes it much easier to then go onto Mars in the future. So, yeah, I guess that answers your question.
Excellent, thanks. There's two more questions in the chat, and then I'll hand over to Oliver. So there's sort of two questions from Dominic M. With nuclear systems, you save weight on oxidizer, but how does the weight of the reactor and cooling systems compare to the weight of the oxidizer? And
Good question. So you get a mass saving from there, but then I also mentioned you need things like disk shields, you need that long structure to separate your engine from your passengers. You need all the cooling systems, typically need a fluid to work those cooling systems to reject that heat. So yeah, there is a trade-off. I haven't been able to quantify it in this study, but that's one of the things that Rolls-Royce are really trying to push at the moment is how do these two types of systems compare, and can we get as much benefit as we think we can by assuming that that dry mass is the same.
Excellent. And the second question from Dominic M is, there's a high failure rate of rockets. How do you mitigate the risk of having a nuclear material on rockets that crash? So that's probably going to tie into some of your experience in hypersonics.
So switch back to the NERVA program. So this was NASA's program to develop a ground a concept of a nuclear thermal. So typically in the engineering process, you don't just design something, strap it to a rocket and launch it straight into space. You design subsystems, components at a very low level, test them in isolation, build confidence that they do what they are supposed to do, and then you build up the complexity of what you're testing. So in the case of this example, yeah, obviously you test all the components and then you do ground testing like the NERVA program was supposed to be doing. And then you can then, once you're confident that your reactor is safe enough, it's had enough test runs, you're confident in the performance, you're confident in the safety mechanisms around the way it operates, then you can integrate it with the rest of the spacecraft, which will undergo its own testing in isolation, and then you'll have much more confidence that you'll be able to launch successfully. So kind of on the flip side to that, one of the things I did the previous year as part of the PONE conference is look into the policy around launching nuclear materials into space. So there's a lot of challenges with policy. So thinking about a company like SpaceX, eventually they're going to be a big global company, have sites all around the world. One of the issues is transferring nuclear materials across borders. So typically, all of the nuclear material that's been sent to space previously has been sent by governments, so NASA, Roscosmos, Chinese Space Agency, etc. Now that we're getting commercial companies to send spacecraft with nuclear materials into space, it becomes much more difficult to legislate that. So, you know, transferring materials across borders, purchasing nuclear material, launching nuclear material historically has been purely government-based. You know, when you launch the Mars rover, for example, that has a nuclear power source on it, and you need the president's permission to be able to launch that. So it goes right the way up to the leaders of the country. Whereas the legislation around companies is very immature. So alongside with this technology development, there has to be a lot of policy development as well to be able to actually make this a reality. So yeah, it's an interesting question.
My question kind of follows that in terms of safety, but rather than safety in terms of a rocket launch going down, it's more the safety to the crew when they're in transit. I know we're not talking about nuclear power generation here, we're talking about nuclear propulsion, but when I think of examples in nuclear aircraft carriers and certainly nuclear submarines where there have been tragic incidents in the past where things have gone wrong and the crew have been exposed to hazardous materials, is that still a risk here, or is it just simply not a fact because it is propulsion rather than energy generation? But if it is a problem, what's been done to explore that problem? Because I know from previous experience, getting safety cases approved and things like this can be an absolute nightmare on programs. I appreciate it's a long way off, but I just thought your thoughts were on that.
It's probably a little bit maybe too early to be thinking about safety cases in terms of nuclear engines for space. What I would say is, you know, in the past, when you've launched astronauts into space, they accept risk. So they know that it's not a completely safe endeavour. You know, not just the launch, but being in space is a very hostile place to be. So you definitely need some kind of human buy-in. There's a lot of safety testing that needs to be done to be able to convince people, especially if it's people like you and me, the general public, to convince people to actually move to Mars and be around these hazardous materials. So yeah, I haven't particularly thought about it in detail myself, but yeah, that is going to be a huge thing, especially if we're trying to send the average Joe to convince them to live on Mars. I think that's one of the biggest hurdles we've got. Thank you.
One last question from the audience.
Yes, with the nuclear electric motor, is the thrust mainly absorbed by the magnets?
Absorbed. So yeah, again, this isn't my area of expertise. Kind of left the propulsion side to Rolls. So yeah, I guess probably can't give you a good enough answer. I'm sure there's a lot of information out there if you're interested in researching it, but yeah, I probably wouldn't be able to give you a decent answer for that.
Yeah, I think in this case it's fundamentally just a case of Newton's sort of second law, effectively. So you're kind of accelerating this mass out of the spaceship, although it's going at very, very high velocity, but it's very, very low mass effectively. But one of the challenges is ensuring like issues with the erosion, because these things are traveling at enormous speeds, and then also neutralizing those so they don't effectively come back to a ship and they've actually neutralized the actual thrust they produce when they exited. But yeah, it's fascinating. So I think this is the last question, so I'll hand it over.
Thank you. So thank you very much. Very interesting lecture. I'm sure everyone was really impressed with what we heard. I think thinking about the questions and the comments that have been made by the audience, it's really that, and what I think you try to portray in your lecture was the recognition of the limitations of what you've done so far. Let's not all get way out of the box too early when we all know that there's a whole load of activity. And I think one of the big things for me, and particularly learning as you go through your career, is learning what the limitations are of the stuff that you're doing, and not kid ourselves on all the time that we've got a really good answer when actually it just showed us what we thought was the case, but there's a whole load of other issues that have yet to be dealt with. And I think that's a really important thing for sort of young career engineers like yourself. And for me, I think it's great to see the aerospace in the broadest sense starting to be handed over from the greybeards like most of us in this room at the moment into the new coming ones. I know there's a couple of Cranfield students at the back who've joined this lecture as well. It's really heartening to see that. I think I can probably see why you got the NERO medal as well, with the presentation. Is very, very clear and very well presented. Thank you. The only other thing I kind of picked up on, and I know it's not exact numbers, but 6.5 months versus 5.5 months to get from Earth to Mars. I don't know how many people in here would actually want to be on that flight, but I don't think I'm one of them yet, if I'm really honest with you. I think I'd get so bored in never 5.5 months, never mind 6.5 months. So it probably wouldn't be me. And I don't know about anybody else if you would like to go, but I don't think I think it'll need to be down to a bit shorter than that before I even think about it. And I very much doubt that's going to happen in my lifetime. So thank you very much for your presentation. So please join me in the usual way and say thank you very much.
Thanks for watching. Please don't forget to like and subscribe. We are closing in on 25,000 space scholars. And stay safe at Astra Pro Terra.